Hello guys, this video is on weak convergence and strong convergence of sequences in vector space in functional analysis. In this video we discuss the weak convergence and strong convergence and the relationship between weak convergence and strong convergence with the help of a theorem. Now the theorem states, let Xn be a sequence in a normed space X. Actually, for sequence we need a normed space because we need to define the convergence in terms of metric. So for that we need a normed space X. Now if the dimension of X is less than infinity, that means if X is finite dimensional, then weak convergence implies strong convergence. In this case there is no distinction between weak convergence and strong convergence, they both are equivalent. Now for example, the vector space of real numbers, dimension of R is less than infinity, it is finite dimension. So in real analysis weak convergence and strong convergence are equivalent, and while studying real analysis we do not make their distinction, we do not distinguish between weak convergence and strong convergence. But in functional analysis, where dimension of X is oftentimes infinity, oftentimes X is infinite dimension space, in this case weak convergence always does not imply strong convergence. In this case weak convergence and strong convergence are different, and weak convergence has its own importance. For example, in a infinite dimensional Hilbert space S, the orthonormal sequences En, the orthonormal sequence En, it does not converge because for n not equals to m, En minus em whole square, this equals to, we get the value equals to 2, and by Cauchy theorem this is not convergent sequence. This can be illustrated in diagram as well. Here the orthonormal sequence, here the elements e1, e2, e3, e4, these elements are orthogonal to each other. So this vector e1, e2, e3, they do not converge to any particular vector, it is a divergent sequence. अब e1 यता जाने भयो, e2 यता जाने भयो, e3 यता जाने भयो, यो कतै पनि कन्भर्ज गरिरहेको छैन. So this sequence En does not converge strongly, but now this f in S dash has a ridge representation. So f of En can be written as inner product En times Z. Now by Bessel inequality, this series is lesser equals to num of Z square, which is finite. This series is bounded, so this series is convergent series. So by the remainder theorem, this sequence En Z must converge to 0. That means f of En must converge to f of 0, and this shows En converges weakly to 0. So in Hilbert space, this Hilbert space S, this sequence En converges weakly to 0 but does not converge strongly to any element. Now let us move on to the proof of this theorem. So again, let me recall the theorem. This theorem gives the relationship between weak convergence and strong convergence in finite dimensional normed space. Since the dimension of X is finite, suppose dimension of X is equals to k, and let e1, e2, ek be a basis of X, then the elements of X, Xn and X has the unique representation in terms of the basis, where alpha in and alpha ai are scalars. Also let f1, f2, fk be the dual basis of X. Let this be the basis with respect to the basis e1, e2. Then we have fi ej equals to 1 if j equals to 1, otherwise 0. This from the definition of fi. Now it is given that this sequence Xn converges weakly to X. We have to show that this converges strongly as well. Now from the definition of weak convergence, for all f belongs to X dash, f of Xn converges to fx. Now since fi belongs to X dash, fi also must hold this condition. That means fi Xn must also converge to fi x. Now let us substitute the value of xn and x. We substitute the value of xn and x as this. Xn is this and x is this. Since fi belongs to x dash, fi is linear. By linearity we get this condition. Apply linearity on both sides. Now from the property of fi, we have fi ei equals to 1, and for all other index j which is not equals to I, fi is equals to 0. So we get here alpha n and we get here alpha I. So alpha n converges to alpha I. All other terms they reduce to 0. So alpha I n converges to alpha I. Now finally, to show xn converges to x strongly, norm of xn minus x, that equals to these two quantities, simplify, use the property of this norm, use the property of norm, lesser equals to this quantity. Now we have alpha I n converges to alpha I. So this term, it converges to 0, and hence we have the norm of xn minus x converges to 0, and this implies xn converges to x, which means xn converges strongly to x. So given that xn converges to x weakly for finite dimensional normed space, we show that xn converges to x strongly, and this proves our theorem. Thank you.